from the UTS to the breaking point, we call this stage necking stage. This stage becomes more significant, right? But for the anneal tempered sample, which is harder, but is less ductile, okay, right? Because when the material becomes harder, usually it's more difficult to be elongated, right? Easy to understand. And then the necking point, the necking process between the UTS to the final breaking point is narrow, right? Easy to understand. So that means how much of this necking process is correlated with the ductility, right? Okay. So another way actually to really define the ductility, how ductile of the metal is, there are several different ways. One commonly used way is we call that percent elongation. Okay, so that means that's a very easy way to measure, right, experimentally. So we define the percentage elongation as what? At the final length of your specimen, when they undergo the testing until the breaking point, you bring back the two parts, putting them together, measure the final length, right? That's an easy one. So that's final length minus the initial length. Initial length, as I mentioned, is usually 2 inch. The gauge length is usually 2 inch over the initial length, right? So this is the way to define the ductility, right? The more elongation the sample can go, then it's more ductile or less ductile of the metal. More ductile, easy to understand, right? So that means it can elongate longer, so that indicates they're more ductile. Say, for example, if we think about the percentage elongation of a pure aluminum, it's about 35%. If you actually use an alloy of aluminum, which has a higher strength means less ductility, right? So the percentage elongation is only 11%. So it's kind of like when you have a larger stress, a larger strength, you will have, the material suffers less elongation, right? So they can undergo less elongation. Another way to define the ductility, in addition to the length change, okay, another way to do is to measure the cross-sectional area, right? There's another way to do, we call that the percentage reduction in the cross-sectional area. So we use the initial area minus the final area divided by the initial. So that one is also another way to measure very easily. You can just use a caliper because we know the original dimension, we know the original diameter is usually ½ inch. And then after break, we know that because of the necking, the sample will become thinner, right? The diameter becomes smaller. You can use a caliper to measure that one. Then you can easily measure the percentage reduction area. Okay? So when you see a larger percentage, see for example, if you see a 70% reduction area compared to a 30% reduction area, which one is more ductile? 70% or 30%? Reduction area. Reduction means that, 70% means what? 70 means originally is this width, later on becomes thinner, right? Much smaller, diameter becomes smaller. 30% means the reduction is not that significant. Then tell me which one is more ductile. The more reduction or the less reduction? Definitely the more reduction one, right? The more reduction one means you elongate the sample more, right? So that these two parameters actually are correlated. If we assume the metal does not change volume during the stretching process. How about that? So there's two different ways to quantitatively define this ductility. One is by measure the diameter change that correlates to the percentage reduction in the cross-sectional area. Another one is directly measure the length, how much elongation you get. The more elongation you get, the more ductile of the sample, right? The more reduction in the cross-sectional area means you can elongate the sample more. That means more ductility of the sample, right? Okay. So another important is usually when there's some defects like a porosity inside the metal, that will usually can significantly reduce the ductility. Okay, so that means if you have the sample have more pores inside them, you will see the percent reduction will getting reduced. Okay, so that means you won't see 70%, you might see 30%, 40%. Okay, because the ductility actually getting affected by that. As I mentioned, if we really measure, say for example, the instant areas during the stretching process, during this tensile step, we can define the true stress, right? So true stress means the force divided by any instant cross-sectional area. So in that case, you won't see a maximum there, okay? During the testing step, you will see the maximum stress you can achieve is at the breaking point. That one is for the true stress, not the engineering stress. Okay? Another thing, for the true strain, once again, true strain is a strain. Strain we use delta L, or we use a dl over L. If you do the integration of that one from the original length to the any instant length, Li, I indicate the instant stage, okay? And then if you do the integration, you will get a log relationship, right? Log Li, which means the final, or at any instant, the length of your testament sample over the L now. Okay, this one is we call it true strain. Okay, or another way, if we think about the volume of the sample does not change, the metal sample does not change, then we can convert these lengths, these instant lengths, and the original lengths to their cross-sectional area, right? Because L non times A non should equal to Li times AI, because the volume of the metal does not change, right? So by that way, if you know the original dimension, original cross-sectional area, or if you know the instant length of the sample and the original length of the sample, then we can easily calculate the true strain, right? So that's kind of like the real curve for the real strain and the real stress, the real strain. You will not see those kind of a maximum point or the UTS point, okay? So now I gave you a few examples here. The real testing, okay? This is a low carbon steel. So after the measurement, these are actually really, but I do not have time to show. What happens is during the tensile stress, after a while, you will see those kind of necking formation, and then finally it will break. Okay? So after the measurement, what you will say, the tensile stress, or that means the point at which it's breached, that one is a 400, or let me say, no, that one is not. The tensile strength here is what? The tensile strength measured here is the one actually in the linear range. Okay, so at the maximum point of this linear range, by measuring this sample, you got 440 megapascal. Okay, and the modulus of elasticity is 205 gigapascal. Based on these two values, can you tell me what is the maximum strain at the end of the elastic stage? Can you do that? Can you calculate that one? If you know, see for example, if you know the maximum stress, oh no, something wrong here, okay. This one should be stress, this one should be strain. If you know the maximum stress, and also if you know the Young's modulus, how can we calculate the corresponding strain? Do you know how to do that? Because the Young's modulus is what? Young's modulus, how do we calculate Young's modulus? Using the stress over strain, right? So that means if in this case, or in the test, in the first exam, if I tell you the tensile strength, if I tell you the Young's modulus, you need to know how to calculate the maximum strain that corresponding to the end of the elastic deformation stage. Easy to do, right? You just use the Young's modulus, or modulus of the elasticity divided by the tensile stress. Or, no, I'm sorry, I'm wrong. It's reverse, right? Use the tensile strength divided by the modulus of the US case. Okay, because, after the calculation, this one is a gigapascal. Take a look. This is the gigapascal. This is the megapascal. Don't forget, there's 1 gigapascal equal to how many megapascal? 1,000, right? So after the calculation, you should get about 0.002, right? Can you guys get that one? Using this one is times 1,000. This number divided by that one is about 2 times 10 to the order of -3, right? So you need to know how to do that, okay? But anyhow, and also this one gives a reduction in the area. You need to know what that means, and the percentage elongation. Percentage elongation for this sample, for the low carbon sample, low carbon means the dopant level of the carbon inside is reasonable low. That usually lead to what? Lead to a less strength but longer elongation. If you do another test, this one is a hard carbon steel. If you compare the tensile strength, it's higher. Okay, it's higher than the previous one, which is the 440 megapascal. If you dope more carbon inside, you can enhance the strength, but at the same time, percentage elongation getting reduced. So that means strength getting higher, the ductility getting reduced. Okay, so that's easy to understand. Okay, so I will temporarily stop here. Let's come back at the 610, and then I will talk a little bit about the hardness